to the second webinar of the series Artificial Intelligence Methods and Applications. This second webinar is dedicated to vision, language, and multimodal challenges. We have a record of registered participants to this webinar. I'm very happy that we have also a fair share of German participants. My name is Matteo Pardo. I work in the Office for International Relations of CNR. I was formerly a researcher in the area of machine learning applied to sensors, in particular chemical sensors, data analysis, and bioinformatics. For 8 years, I was the scientific attaché at the Berlin Embassy in the Italian Embassy in Berlin, and I'm co-hosting this series with Vincenzo Fiorentini, who is my successor in this role, and he will give you also a welcome in a short moment. I'm very grateful to both our speakers today, Rita CUCCHIARA and Professor Rita CUCCHIARA and Professor Sebastian MÖLLER. The house rules are that both speakers will have a time between 30-40 minutes for their presentation. At the end of both presentations, we will have questions. The question you have to write them on the right-hand side. You have a field domande in Italian, and probably in the German version it will be questions or maybe domande. I don't know if it's translated. There you can write your questions. I will read them to the speakers, and they will answer. First, I give the word to Vincenzo for introduction on his side, and then I will introduce the Rita CUCCHIARA, who will speak first, and then Vincenzo will introduce Sebastian MÖLLER after that. So please, Vincenzo.
Good morning, Matteo. Good morning, everybody. My name is Vincenzo Fiorentini. I'm a science attaché at the Italian Embassy in Berlin, and in real life, I'm a university professor of physics. So, I'm not completely an alien. So I bring the greetings of the embassy, the ambassador in particular. And I think that's it. We can go on with our proceedings. I look forward to a productive meeting.
Okay, thank you very much. So the first speaker is, as I was telling you, Professor Rita CUCCHIARA. The title of her talk is From Visual to Multimodal Understanding. Professor CUCCHIARA has a master's degree in electronic engineering and a PhD in computer engineering both at the University of Bologna. She is professor of computer vision and cognitive systems in the Department of Engineering Enzo Ferrari, a name that I believe will ring a bell, at the University of Modena and Reggio Emilia in Italy. She is directing there the Interdepartmental Center of Artificial Intelligence Research and Innovation. She is also a research associate of the Institute of Informatics and Telematics at the National Research Council, so at CNR. And there she has a leading role in the FAIR project, which is a network project under the lead of CNR, relatively big projects for Italian standards, financed with money from the Resilience Fund, the EU money from the Resilience Fund. She's directing the modular unit of ELLIS and coordinating new projects named ELSA and ELIAS of Horizon Europe. She has served as president of the Italian Association of Computer Vision, Pattern Recognition and Machine Learning from 2016 to 2018, and thereafter as director of the National CINI AIIS lab. She collaborated with the Italian government for the national strategy in AI. Actually, if I'm not wrong, she was part in both panels, the one from the Ministry of University and Research and the panel of the Ministry from Economic Development. So she has a unique position there. and she is a member of the advisory board of, for example, of the Max Planck IIS, and she's a member of the board of directors of the Italian Institute of Technology, as well as other our institution and associations. She is active in the organization of scientific meetings, big conferences. She was the general chair of several conferences, ICPR, for example, or ICCV, and others. So Rita, the floor is yours, and let me give you also the electronic floor.
Mm-hmm. Okay.
Okay.
So may I show my screen? Do you see that?
Yes.
Okay. Thank you very much. Thank you for the long presentation. It's too much. Yeah, and good morning to everyone in Italy and in Germany. Ich spreche keine Deutsch, so I studied in the past, but now it's better to use English or Italian. I'm so sorry. Do you see also me, or do you see just only the slides?
We see the slides and you.
Okay.
But in impostazione di visualizzazione, maybe you can do what you did before.
So I say.
Exactly.
Yeah.
Yes.
Okay. Okay, now I don't see you anymore. I see just only my presentation. So if
Okay.
there is something, please tell something, and also to close my time, because I know that. Good morning, everyone, again. The title was very large, because from visual and multimodal understanding, more or less, could contain many things in computer vision. And so I selected for this presentation of today just only something we are doing in IBEG Lab in Modena in the last time. I have a number of slides, so probably I will skip some of them, but I will leave them, and they will be available also in my website in order if you want to take them. So that's starting to the fact that the computer vision research area, where I'm working in this area since my thesis in 1989. So this area of computer vision is so large, it's becoming larger, and it's becoming larger also in a multimodal setting. So what does it mean? It means that we are studying new system, now trainable system, because are strongly based on machine learning, with capacity to understanding both visual and textual modalities, generating visual and textual modalities, and for possibly acting in real worlds. We don't speak about that acting part because I have no time, but the idea to work together visual, text, and navigation is something that is now really interesting. There are many reasons to do that. From one side, also in our brain, visual language and also action are really very connected, both in the cortex and in the middle brain. So it's something that now we are studying to do similar things, and also because it's doable, since now we have available many data sets that are multimodal and annotated or not annotated for supervised or semi-supervised learning. And the third reason, at least for me, is that there are now many projects that are working on that. I will talk about 3 of them. In particular, we are working in an Italian project called Creative, that is financed by the Italian Ministry of University and Research, together and coordinated by Roberto Navigli in Sapienza, and together with the University of Trento. I will talk a bit about ELSA project. I'm not coordinating the project, just only the Modena unit, but together with Leonardo, we have in charge the work package or multimedia for understanding deep visual data. So it's something I will take, discuss a bit, and especially these are the topic of this new project that Matteo cited at the beginning, that is called FAIR. FAIR is really the important project for Italy because put together many university, companies, research centers like CNR or IIT, and working working in foundational research of artificial intelligence, and myself, together with Roberto Navigli, are coordinating one of the transversal project about actually visual language and multimodal challenge. So this is really a topic that for Italy now, it's important, and also for me. That is the sort of agenda of my presentation of today. I will start with the part that is really just only visual, so computer vision, visual understanding, discussing something about the visual transformer, and then I will move in the direction of describing vision data by text. So the problem of captioning is something we are working a lot in the last 6 years in Modena. And so I will discuss with you just only a few things, in particular about controllable captioning and measuring captioning. That is also something we will present in the next CVPR in Vancouver this summer. And if I will have time, I will give you just only a very short information about what we are doing for detecting fakes in multimodal setting. Okay, so let's start. What is the visual understanding today? So it's the strong part of computer vision, because when we see an image like this one, we see a lot of things. And in general, when we want to understand, then we try also to use our language capabilities to describe what we see. Sometimes what we see is not actually the real things that are, but if I see an image like this one and I don't know, Pretty Woman movie, I could say that is an elegant, rich and respectful woman that is walking together with a lot of packs and after a long day of shopping. So everything of that I can understand by an image like this one. Or in an image like this one, I can understand something about the young Californians people and so what they are doing, possibly strange, but there are many things that I can say looking at an image like this one. So we can understand very easy how much is difficult computer vision now. And the typical approach of computer vision in 2020s is that we try to learn many information from the image, coming from the data, coming from the models. So the models could be visual models like just only elements like people or vehicle or something that is not in the image, like a basketball, I don't know, or also verbal models like the concept that we have. Then what we try to do is to put everything together, possibly the models and the data in a latent space, in order to extract them many different task result. Vision is not only perception, it's also understanding, it's also recognition, identification, but also reconstruction, and also prediction that in Italian is prevedere, so is seen before, or imagining, so that is creating new images, or also hallucinating, that means creating some images of something that do not exist. That is the sort of the starting point of generating. In one word, I say something that Leonardo called 500 years ago, l'arte suprema del saper vedere. So the capability to understand what we see. Probably now AI-based large-scale model do not know what that are seeing, but they can see actually. They can see partially because computer vision is not a solved science, but there is a lot of things to do. Even if in these times, the basic idea is to encode the data, images, but could be also text, audio, and many other data in a latent space data representation, and adapt this latent space data representation in many different downstream tasks, like actually classification, understanding, prediction, and generation. And the classical techniques we are using now for doing this kind of things is actually transformer. Transformer has been used in language, but now they are used also in computer vision. Probably also better than convolutional neural network that are more natural or more suitable for images. In fact, 2 years ago in ICLR 2021, the idea of using a visual transformer, so a transformer for images, where the images are divided in patches, are projected in a space, also with the positional encoding, and represented is a fantastic way to represent also data, especially because they are parallel, is scalable, and from one side there is an infinite receptive field, so all the data can be connected together. This is working well, and the transformer encoder is, I say, a classical transformer, but so very similar to the other one, but what is changed is the input data. This is really working well. This is one paper that has been presented yesterday in arXiv that proposed to use a visual transformer for, no, not DETRA in particular, for real-time object detector, showing that for this capability seems to be absolutely better than YOLO. I didn't have the time to test them, but it seems that is really very interesting. So many researchers in computer vision are trying to understand if transformer in vision is good and how much is good, and also can be modified. I would like to show in a few minutes what we presented, what we did last year, that I think is interesting as an idea, and also the results are not bad. That is the idea of using in the transformer also some concepts that are typical of CNR, so of computational, of convolutive neural network. Because if I think to transformer and visual transformer, they have also some drawbacks. From one side, the computational costs are very high because we need to have a very long sequence of layers. The memory consumption is very large, and also there is now actually this hierarchical representation that is typical of convolutional neural network, the pyramidal representation that is working so well in computer vision. So what we present is the idea to put to put a bidimensional max pooling concept together with the width. I give you an example just only with the image that probably is easier to understand, and the details are the paper where my PhD students last year won also the best paper awards in Italian conference ISHAP, international conference ISHAP. So that is if you take the image, you can take the image in a classical transformer. This is similar to the width, but without the CLS token. Then in the transformer layer, we add a part, and this part is actually the 2D max pooling layer, like in a convolutive neural network. And then this kind of things can be used in order to reduce the complexity, reduce the dimension of the data, and also to keep the spatial relationship. That can be done in the first transformer layer, and after then there is the average pooling and so on, and we did for classification, but can be used for many other tasks. Or you can put it in the second stage where the features are higher level, in the third stage or in the fourth stage, and also in the middle or in the difficult or everywhere if you want. And so we studied which is the result, the better result, without the time, but just only we'd like to give you few information. If you use this convolutive concept inside the width, you can have two different advantages. The first is the enormous reduction of floating point operation needs. So it's easier and faster to work on that. and especially if you use it in the first layer of the transformer. Instead, if you pull it in the last layer of the transformer, you achieve again a reduction in time, but also an improvement in accuracy. So these are the results that probably can be better represented in this manner, because you can see that if you use this both visual and convolutive approach, you can have the better of the two approaches and gain in speed or in complexity and not lose in accuracy. This method actually has been explored in many different times, and just for your information, this is another enormous idea, different of our, to put instead a transformer in a convolutive neural network that from one side is very interesting, because also in this case the results are really, I suggest you to read this paper if you have the time. Okay, so I can spend a lot of time discussing with you about visual transformer, about the part of computer vision, but instead I would like to move in the multimodality. So in the idea to use vision and text data together, or in the first time to start from vision and to arrive to text. This is a problem that is called captioning, since now we know very well that also with the GPT-4 and many other, we can use a visual or language as a prompt to generate description text. This is a first part of this mechanism, that image captioning aims of extracting a short and synthetic description of the image using text. So with the first part, it is a visual feature extractor, and the second part that is a language model. This has been presented for the first time in 2015 using a convolutive neural network as a feature extractor, and using LSTM as a text generator. And many interesting papers has been presented and used for this kind of things. All of them with this concept of show and tell. This is a term that has been proposed by Joshua Benjo and the other 7 years ago. The idea of starting with visual data understanding and then going in the direction of natural language generation. If you are interested in this topic, we published last year a long survey on that, on PAMI, that of course, since it's from 2 years ago, does not include the new methods, but is general enough that for people that starting to work on this area, especially because we discussed many different methods of visual encoding, many different methods of language model, and also many different methods of training and training strategies. Now, transformers are very useful, and we did many modifications of the transformer in order to be more suitable for the problem of text generation. For instance, in this work, we presented a CVPR 3 years ago, in 2020. That's called M2. We added in transformer 2 different things: a memory and also a mesh connection. In few words, the mesh connection is, I say, very similar in some sense of the UNet, or the capability to have a skip connection between layers in order to take all the features, low level and high level feature, together in the step of generation. And instead, the part of memory augmented encoding seems useful for keeping and for having the memorization of some concepts that have been trained before. Actually, this method was really very interesting. and reused in our community, since many different approaches, starting from the idea of using memory and this cross generation have been proposed at least at that time. So that time means in 2020, this method was the one receiving the best result in the COCO leaderboards. For the people that are not expert in this field, COCO dataset is probably the only one dataset that people working in image capturing are using, because COCO has an enormous amount of images and with 5 different captions written by humans. So it's something that can be used both for training and also for evaluating. Unfortunately, general textual description are a bit noisy, so I don't believe that COCO is the best data set to learn and also to use, but from one side is the one that all the community use for comparison. And since we are trying to compare at the end strings of text, the classical measure like BLEUR or Meteor that are used in text analysis are used, but in the field of captioning, CIDR, the last one, is considered more interesting because is related also more with the human perception of what. So it's not just only a syntactic comparison of text, but take into account also the image. And so in general, we use CIDR as a data of that. But if you take some qualitative result, probably it's better look, for instance, this cat. The ground truth, one of the ground truth is a cat looking its reflection in the mirror, and with them to transform, we can achieve the same, I say, abstract concept to look at the reflection in the mirror. I say abstract because actually we know that it's just only a generation of text, but a generation of text that is really interesting in this case. As well, we can also integrate the we can also integrate the visualization step in order to understand what the network is doing in order to generate text. And so we can also see where the transformer put the attention while it's generating a single images. So in order to understand also a sort of explainability of the method. And then this is actually has been has been used also in as I say, in action explanation to understand what the robot is doing while moving. For instance, extracting caption of what the robot is saying. And this is useful for interaction, human-robot interaction, but also for reverse engineering and understanding what the robot is doing while moving. So in this case, the robot acquired the image, send the image to a server, provide image captioning, so multimodal understanding, and report and reports in a text what you see. Okay, this was a basic classical idea of captioning, but now captioning is evolved a lot in the last few years in many different trends. So for instance, with the idea to captioning also with the details that have not been annotated, so in novel object captioning, or in the direction of prompting to create what's called dense captioning, so a caption that is larger and is not just only single sentence, or a diverse captioning to say, okay, it can generate many different captions also in multilingual, and personalized means, for instance, with a different style. Or what we did, and also many other people actually are doing, is instead to work on controllable captioning. I like a lot this idea of controllable captioning. What does it mean? Controllable captioning means that if I want to see something and I want to describe what I see, it's not necessary that I describe everything, but it's better that I can have a focus and a goal in order to describe that. So we try to understand if it was possible to guide the captioning according to some region or something. Many approaches have been done in this field that in general called attention-based approaches, since attention, really attention, not attention in the term of transformer, but attention in the meaning of human attention. So considering what the human do when provide a scan path or provide attention in some part, look in the image, and then extract a caption according to that. We proposed a few years ago this method called show, control, and tell that is able also to control the caption. In order to do that, we don't use a single word, but we use a noun chunk. Noun chunk is a noun grouped together with its modifier, the adjective or something like a young boy or a cup or the article or so on. So we work at this level because in order to represent the attention, it was good to have not a single word but similar things. And a few years ago, we proposed an architecture at that time based on LSTM that was composed by two parts. The first part was able to extract some interesting region. Then there is a control signal that is able to understand which are the parts that should be represented. No, come on. Okay. That is just only, for instance, a detection sequence. I say I would like to represent and to describe before the part in green, and then the part in orange, and then the part in blue, and then provide a mechanism to insert this type of attention in the sequence of generation. Now we do the same with the transformer also, of course, with a better result. And this is something that you can see probably in this result more than the number, because the number you can read if you're interested. For instance, you see that if depending of the region of attention that you put, also the description is different. Like a young girl is sitting down with her dog, or a woman sitting on a table with the dog eating a cake, or so on. So I say that in this manner we can control the multimodal generation of that. These are many other examples that we can have of the same situation. This is last attempt is to put together style and style captioning, separated them in the learning phase, but using them in order to enlarge the capability of this model. This is is what the new language model are doing, but instead of reuse and spend 4 million euros for each training, we use a pre-trained network like Clip, and then we use them in order to improve many methods. Since now I'm I already spent more than about half hour for discussing with you about them. I'm skipping this part, but if you want, I can discuss after. That the idea is to put together a foundation model like a Clip with the transformer encoding and then transforming decoding, and we trained them on 36 million of image text pairs, unsupervised, so very noisy coming from the web, with a large use of the CUCCHIARA supercomputer center, and results are really interesting. I can just only use this image to show you the result, because we can have some emergent behavior that is, for instance, to describe what they see also with the name or with the action, even if it was not annotated by human. Like, for instance, this is not only a bridge on over a water, but it's the Golden Gate Bridge in San Francisco. And so this emergent capabilities comes from the unsupervised learning of this two steps. Okay. Just only two things before ending. The first is the metric we are using for captioning are not good enough, because I told you they are based on just only on the comparison with this few annotated data in COCO, so are not enough, and also are not well representing the human perception of that. We should insert human feedback in the evaluation, but probably just only OpenAI can do is acquiring 100 million of people for that. We have not this number of person that can give us a hand. So we use a new idea. This new idea is to try to see a new metrics for understanding if this caption is good enough. Matter is a classical measure of language model. CIDR is a classical method of measuring of captioning. CLIP score means let's use a foundation model to see if there is a correspondence between them. But what, like, for instance, to say, okay, this is a silver bicycle parked in a living room. But if we put some more detail, like a silver bicycle leaning up against a kitchen table and chairs, that we know that it probably is better, this measure are not able to take into account this difference. So we presented this new measure that is called PAX, that is very closer to the human feedback, and this will be presented, as I told you, in the CVPR in July. Just only in one image, what we do in this manner is a very complex system, because instead of using just only a CLIP score, we use also synthetic data generation using stable diffusion, and using also the generation of the text generation of synthetic generation. So we put a lot of an additive example that have been augmented with the synthetic data in order to train this measure probe that seems to be absolutely better than the other one that are and can be used both in image and in video. Again, if you want, I can spend more time after on that in the question, but the idea is that with this method, probably we are closer to the human capability to represent the video content in the image. Look, for instance, in this case, if we say that this is a baby elephant, it's not a baby horse, every human can understand that this is actually an elephant and not an horse, and our system that has been trained in enormous amount of synthetic couple, image and text can be done. This is the interface that, if you want, you can try, that is on our data set. Matteo, you have just only 1 second, probably, or not, to put the attention to another topic that is really very connected on that, because we use actually the same technology, that is about fake detection. As you said in the last images that I showed you, this one, we use synthetic generation. We use images synthetic generation because this was real images, and this has been a synthetic generated image, and we use text and also generated text. generative AI is really very important in industry, very important in design, very important in many things. Just to give a publicity today, there is the Salone del Mobile, so the big fair about furniture in Milano, and we will present our AI system for generating ceramic tile with generative AI for furniture. So it's something that can be directly used, not only for, I say, for fun. But for fun or not for fun, there are really many images that are being generated, and the problem to disentangling, so to understanding if they are synthetic or not, is still a problem. We proposed this method that is divide the semantic and the style, so the semantic and the perception. And until now, what we can say is that now with the stable diffusion 1, stable diffusion 2, and so on, we are able actually to recognize the synthetic data because we are able to divide them. I say that it's very close to the other concept because actually in order to do that, we use clip and we use text generation and semantic generation. Since we need the data, we generated a new data set that is called CocoFake, where starting from one image and the text generation, we generated millions of fake images that are sort connected to the original one. This is a new topic. We will have for this a new workshop in ICCV in Paris in October on that, with an enlarged community, also with the people from Meta that are working on the same area. That idea is, okay, starting from this original true image, we generated a lot of synthetic image represented by the text, that is a true text used for describing this image. And then the problem is to understand which is the original one and which is the fake one instead. Results are interesting, and I have no time, but what I say is that until now, if you don't use a large compression like JPEG, using Fourier transform, using old style image processing methods together with the training system, is able to find. And so we trained a classifier. Also in this case, we have a very new interface that you can find on our website, because you can load your image and the system actually is able to predict if this image is fake or is real or is not. And until now is working really well, but the time is long and the generation is becoming more sophisticated day by day. Okay, this is my conclusion because my time is over. Which are the conclusion? Probably we should discuss a long time, but I would like to give a few conclusions. The first is that until now, in these days, we see that the approaches of attention-based, like transformers, seems to be really very suitable also for vision. Probably could be improved, could be better tailored for visual data with respect to the textual data, but is really working well, and is working well in identification, in recognition, in classification, but also for keeping the perceptual similarity. So we use, for instance, for this problem of deep fake detection. And the second is that transformer is perfect for multimodality, so we use is a plain form or together with clip or in many other methods to describe vision by text and generated by text and vision many other things. And also, of course, in this case, a new problem calls for new measures, and so we are working on this data. Okay, concluding, these are people working with me, but actually as well Marcella, Lorenzo and Silvia that are researchers working with me. There are also at least 10 PhD students that are working in this area, and I would like to thank all of them. I'm stopping here.
Okay, thank you very much, Rita. I see that there is a lot more to say, but we need another webinar probably for that. So I will give the word to Vincenzo for introducing Sebastian, and then question at the end. Sebastian gave the slides ahead of time, so you can download them on the right-hand side. You can, under Documents, Documenti, you can download Professor Möller's presentation if you want to have it already. I will send all presentations, as always, to all people registered, and the link to the registration of the whole webinar, to the recording of the whole webinar, to all the people registered. Please, Vincenzo.
Okay, so we come to the German side of this meeting, and our German speaker is Sebastian Möller. He's a professor for quality and usability at the TU Technical University in Berlin, and he's also the leader of the Speech and Language Technology Lab at the German Center for Artificial Intelligence, DFKI. He's a graduate of the universities of Bochum and Orléans, in France, and Bologna in Italy, and worked at a number of places before becoming professor at TU Berlin in 2007. And so, more or less following in the topical area that we have already explored so far, Sebastian was going to talk about designing social, explainable, and trustworthy speech and language technology. Please, Sebastian.
Thank you very much. I'm not sure whether you can see the slides now.
See a blank screen right now.
Blank screen.
Okay. So I will try to run the sharing again. It worked before.
No, let me try again. So. We tried that before and we could see the slides. Now we see a blank screen.
Okay, I will try to run again this one.
Okay, now we see your screen. Great.
Okay, that's better. This way.
Is it freeze? No.
It says paused. Okay. Let's try again.
Yeah.
All right.
Okay, thank you.
Great.
Sorry for the slight delay. I'm very happy that we had such a great overview of the visual and the visual and textual aspect of AI in Rita's talk. Actually, I've noted that many of the methods Rita is using are very common also in speech and language technology, which is the topic we are focusing on at DFKI. And if I say we, there are a number of colleagues which are mentioned here on this slide who contributed to the content of this talk. Now I will move a little bit from the visual part to speech and language, to the spoken and written language, but with a slight focus on social, explainable, and trustworthy AI, which are aspects which are frequently neglected, but which I think are very important if we really want to make AI which is usable for a wider variety of the population. Because if we talk about AI, and you have seen that in many slides just before, but even otherwhere, then we are talking about deep neural networks, which consist of a couple of layers, and where the information is somehow treated, aggregated, recursed, and at the end we have an outcome. And the big question is, what does this outcome mean? why is the outcome good in many cases and not so good in other cases? What information is contained in this outcome? And can we perhaps diagnose the performance of such a neural network in order to find out which aspects of the input space are well treated and which others are not so well treated? And that's particularly important in the domain of speech and language processing, because in speech and in language, you do not have only the linguistic content. We have quite a lot of other aspects of the speaker, of the writer, of the emotions, of the personality, of other traits and states of this person who is producing the speech or the text signal, which might be very important and which have to be distinguished from the pure literal lexical content of what has been said or written. So the focus we are having at the DFKI is in general human-centric AI, and this is part of a true human-centric artificial intelligence. So I will try to address these three aspects of social AI, explainable AI, and trustworthy AI with different examples. In social AI, we'll rather work on the speech signal, in explainable AI rather on the text level, and then with trustworthy AI, we go a little bit to a different use case, a medical use case. And I try to stick to the 30 minutes which we have. So in speech, there is, apart from the linguistic content, quite a lot of information about the speaker. For example, the social characteristics of that speaker. We know from psychological studies that speakers show two main traits which are called warmth and competence, and which are particularly important if you want to use synthetic speech in particular application scenarios, for example, in care scenarios, health scenarios. Warmth and competence are very important to convey information and to make technology, especially assistive technology, acceptable to humans. Now, our first focus was on finding out whether we can produce such warm and competent voices also with deep neural networks. And this is why we first did a perceptual study about whether warmth and competence can at all be found in something which is produced by a neural network. We came up with a larger set of attributes, and we found that actually those two well-known factors from sociology and from psychology are that they are also visible or audible, I should rather say, in synthetic speech, and that you can describe them. So we built questionnaires for this purpose, for both for warmth and competence, then try to analyze the corresponding speech signals with respect to what information from the acoustic speech signal is really important for producing a warm impression or a competent impression in the listener of synthetic voice. And then our question was, can we put that into a neural network? Can we force a neural network to produce warm and competent voices? There are two approaches for this. One is called voice conversion. That is, we try to transfer spectral characteristics which are mainly important for the identity of the speaker to another signal while maintaining, for example, the identifiers of emotions or of personality, of warmth and of competence in the speaker characteristics. That's one way to do it. I omitted the audio signals here because usually they come up poorly through this kind of web connection. So I just highlighted some spaces where you can find them on the web. The other approach is to directly manipulate the synthesis process. So we try to manipulate the synthesis procedure of a well-known tachytron neural network-based synthesizer, which is state of the art nowadays, and try to force the synthesizer to produce warmth and competence speech samples. And that's actually what is possible. Both approaches are basically possible, and we are still comparing them in order to find out which is the better way to force the synthesizer to produce speech samples with certain social characteristics. On the other hand, we have the opposite problem, that we have natural speech which has these characteristics and which we need to analyze, while in frequent applications we have to deal with the identity of the speaker. And we have, for example, a collaboration with the Charité University here in Berlin, who has a hotline for people who are suspect to commit child abuse, and they have a help hotline. And people refrain from using that hotline because they think they are identifiable through their speech. So the plan is to anonymize the speech so that the identity of the speaker cannot be recognized from that speech. But in turn, we want to keep all those what we call the meta communication aspects or paralinguistic aspects of the speech, like the emotion, the personality of the speaker, and so on. We want to keep that content intact. So we want to disguise the identity of the speaker, but keep the other relevant context, which is very relevant, for example, for a therapeutical discussion amongst two people, to keep that information intact. The same applies, by the way, if you want to make data usable for other purposes. If you want to be GDPR compliant, you need to make sure that either you have the permission of the origin of that speech signal in order to be distributed, or if you don't have that, you need to be sure that you can appropriately anonymize the identity of the speakers. And that is two requirements, either to do that offline or to do that online in a real-time call, for example. So we analyzed what are the important aspects which need to be kept and which others should rather not be kept, and then try to again use a neural network. In this case, we use generative adversarial networks, also something which is well known in the visual domain. We use that for the speech domain as well. So networks which can generate samples with certain characteristics, and the characteristics we want to have are the emotional content of the original speaker, are the personality of the original speaker, but we don't want to have the identity of the speaker. So we don't want to know who was the person who uttered this utterance. And we need to check that, of course, and we check that with another AI-based tool, namely a speaker verifier, speaker verification system, which tries to actually find out who was the speaker producing it. And you can use such a system in order to train your generative adversarial network in order to produce signals which keep the emotional content, keep the personality, keep other traits of the speaker, but disguise the identity of the speaker. And that can be done in a rather automatic manner if you have the appropriate neural network architecture behind. So that's one of the systems we are currently working on. I mean, I don't want to go into the details here, but just to show that you can try to put certain wished characteristics into the output of such a generative network, and you can train the network to forget about, to ignore other characteristics which you don't want to find in that output. Sorry. Of course, it's not only important of how it is said, but also what is said. So if I utter the statement, "My name is Sebastian Möller," then even if you disguise my voice, you can still recognize that it was Sebastian Möller. So of course, we have to also work on the textual level. So we do need to go on the textual and on the speech level. If we have discarded some paralinguistic aspects, then we still need to find out what is in the lexical content of the words in order to disguise that as well. And that's, of course, very important to make a comprehensive framework of taking into account social characteristics, identities of speakers, and so on in AI. Now, the second aspect, explainable AI, which is a well-researched topic nowadays, but not so much in the speech and language domain. Many of the approaches we have come from the visual domain, and in the visual domain they work quite well. You have seen in some of Rita's slides highlightings of areas in a picture which were responsible for provoking a certain decision of the system. And this is something which is not so common, or has not been so common in speech, and especially in text processing. although there are some approaches for doing this, and we have worked on that as well. Now, the first question is, what means explainable AI? Whom do we want to explain something to? And of course, there are differences in whether I want to explain the functioning of a neural network to an expert in neural networks, because he can deal with layers, he can deal with architectures of the networks, he can see the impact of certain parts of the layers or certain steps in the pipeline on the outcome of the network. But a user of such an approach would never be able to do that. A normal user, a naive user, would not be able. A regulatory entity needs other aspects in order to explain how a model behaves, for example, with a large range of the population, with diversity, with non-discriminative behavior, and so on. A manager, an executive board member, needs other types of explanations in order to understand what the AI is serving him or her. So the first question is, who is the target audience of XAI, of explainable AI? And in many cases, the approaches we have are only tailored to real experts in neural networks. Then we need to say, what do we want to convey? What information do we want to convey? Explainable AI means that we want to have explanations, which is a collection of input and intermediate features that have contributed for a given instance to produce a certain output of the network, to produce a certain decision. That's something which is perhaps enough for an expert in neural networks, but it's not understandable. It's not something a naive user can understand. So we need an interpretation that is a mapping into a domain the user can make sense of. And then both together, the explanation and the interpretation are forming what we call transparency. And then this transparency may give the opportunity to the user of an AI system to also predict what a model would say with some unknown input. So what we call simulatability, the capacity of a human to learn to predict the behavior. Imagine someone who needs to control fake news in a social media enterprise, and this person needs to understand how such an automatic support tool would help in guiding a decision which in the end needs to be taken by a human. Same, for example, for a medical doctor who makes use of an interactive support tool for diagnosis. He needs to understand what are the reasons and why is a system which wants to support me in my medical decision, why is that system taking a certain prediction? How would the system behave if I change something in the input space? So we have worked on these aspects of explainable AI with respect to text mainly. So here you see an example where we want to diagnose what goes wrong in machine translation. So we had samples of source sentences, machine translation, and human gold standard translations. And we then trained a classifier in order to identify as the words which are responsible for either classifying a translation as being made by a machine or being made by a human, in order to find out about the differences between these translations. What are the things a neural network would use in order to classify a translation to be produced by a machine or human? And with this, we wanted to, of course, find out what are the problems of machine translation, of nowadays machine translation, and how can we improve it? What grammatical structures need to be taken into account? This is good for someone who develops machine translation system, but it's not really usable for a general public. So what we would like to have is a more wordy explanation of what takes a classifier as a criterion for a decision. So for here, for example, we have they have a sentiment analysis on movie reviews, and the sentences here, the phrase "just be the worst movie ever produced," are important for the prediction that this is probably a negative sentiment towards this movie. So this is something which is rather understandable to a normal user of a movie review system, for example. Now, ideally, we would like to turn all these what we call heat maps, so the visual equivalences of explanations into something which can be better captured by a human. For this purpose, we first developed a large repository of methods in order to produce these heat maps. That's our thermostat toolbox, which is used widely nowadays, I think. It's openly available. And now we use these different ways of producing heat maps, of producing highlightings in the text in order to come up with wordy, with textual and ideally conversational explanations. So we would like to have a system where the user can ask, why has the system come to a certain decision or to a certain prediction, and then the system would be able to answer back to that. And that could be in a back and forth communication scenario, something like here, what are the top 3 features for predicting, this is a medical use case, as you see, diabetes in the data. And then the model would say, okay, the topmost features are glucose, the body mass index, and the diabetes pedigree function. And then you can say, okay, if the body mass index isn't important for the data with a BMI greater than 40, what does the model predict? Is it likely or unlikely to have diabetes? So I can ask the model about explanations of why the model takes certain decisions or predictions, which might be helpful for the user. So our framework we developed for this is called the mediator framework, where you have a kind of moderating entity sitting in between the human who needs explanations for something and the model, which ideally has these explanations built on top in terms of heat maps, but these heat maps need to be communicated to the human, and that's this mediator which tries to generate this explaining dialogue. So a real interactive system where the user can ask the AI system, why did the system come to a certain decision, but also questions like, how would the decision be different if I had a different input space, if I had different information at the input, if I have different measurement data, for example, for my medical use case. So the user can ask the system about what would the system do if I had a different input. And that really helps explainability and simulatability in the input space. Now, to conclude, I would like to come to this idea of trustworthy AI, and I would come back to the medical use case, which I've already used a number of times here. That was a project we did together with the Charité hospital here in Berlin and a couple of other partners. They wanted to find out about the probability of kidney transplant patients to have some complications. And they wanted to have that with a system, with the help of a decision support system, which is trustworthy. Now, what is trustworthy? According to the European Union, that's a definition from an expert group of the European Union, criteria for trustworthy AI systems are that there is human agency and oversight, that there is a technical robustness and safety, that there's privacy and data governance, that there's transparency, one of the criteria which I've just shown you. There's diversity, non-discrimination, and fairness. There's societal and environmental well-being and accountability of the system. And in the project which I describe here, we basically addressed 4 of these criteria, which you see highlighted here. So the question is, can we support medical doctors in taking an important decision, namely about possibly complicating factors of a kidney transplant? And the idea is that we wanted to make that in a human prediction way. That is, we asked doctors, given the data of actual cases which had been collected in the Charité hospital, how would they estimate the risk of having a death-censored graft lost, or having a rejection of the transplanted kidney, or having an infection of the kidney, and to perform such a prediction for a period of 3 months, 90 days. That is the task which is given both to humans and to an AI-based system, and then to a human supported by an AI-based system. And the the logical question behind that exercise for us were, how good does a system need to be in order to be helpful? How good can clinicians solve the task? And is an AI-based system any better, or is the combination of a clinician and an AI-based system any better in that task? And then also, how should such a system be designed so it can influence the decision of a clinician in a positive way and not in a negative way, of course. We came up with a dashboard, which was the outcome of a couple of user-centered studies. You see, it's a rather, on the first side, easily understandable dashboard, because you have a flow of a patient over a time range here of a couple of months, so from 2011 to 2012. And it gives a risk score, so an aggregated score of the risk for one of those endpoints, we call them, so the graft loss, the rejection, or the infection of the kidney. And it gives you an indication, green, yellow, red, whether this is something which is high risk or not. And then at the same time, it includes several features which are used in order to produce this risk score. Features which can be interpreted by a medical expert, not by myself, but by a medical expert. So some local lab values of certain analysis here, and some global features of the background of the patient, which are taken into account in producing this risk score. Now, the doctor then has the overview of this dashboard about the status of the patient at different points in time. That were the points in time when the patient visited the hospital, and then he comes up to this risk decision and needs to find out, is that something which is reasonable? Would I have the same decision without the system, or is it something I should rather ignore? So first we tested how is the system, an AI-based system, alone on this task, and we found that depending on how much prediction period you take, so it's 3 months or 6 months or 1 year of predictive period, and on what type of endpoints, the rejection of the kidney, infection, or the graft loss, we reach rather good performances. It's not that we say a system with 77% accuracy is enough, no, but we reach rather good performances, especially to state-of-the-art baseline systems, as we have found here. So that's the AI-based system. Then we collected data from medical doctors without the support of the AI-based system, and then afterwards with the support of the AI-based systems. So the physicians, and we had 4 junior and 4 senior physicians who had some time, normal time, to read the data of the patient and to form their own impression, and then to make a prediction, which is a rather unusual task for a doctor to do such a type of prediction. Usually you have to take an instantaneous decision about a treatment, for example, or therapy or risk. So they needed to guess that, and the key findings were that in the end, the AI did better predictions than the medical doctors, at least for the selection of doctors we have. So I would not say that AI is better than doctors, not being said that, but in the study we had here, the AI outperformed the medical doctors. Then we found that the junior medical doctors performed lower than the senior medical doctors, which is something you would expect, that someone with more experience in this particular field would have a better chance of predicting, for example, risks in a patient than a junior doctor would have. What is then more important is, then if you give the dashboard to the doctors, if you give the this colorful thing with the values below to the doctor, then junior doctors increase in performance while senior doctors decrease in performance. That is, apparently the predictions from the AI-based systems are helpful in the way they are communicated to the junior doctors, but they are not so helpful to the senior doctors. Now we can guess why should that be the case. Are senior doctors less flexible? Don't they trust in AI at all, or something like that? But we think that it shows that the explanations we want to give with such a system, they should be tailored to the user group. One of the things I said at the beginning when we talked about explanations, this is a very important aspect. But it shows that also decision takers, like medical doctors in this case, they can be influenced positively by the prediction of an AI-based system. And then the question is, how can you optimally combine the decision capability of the doctor with the detection capability, let's say, of the AI? And what is interesting is the medical doctors and the AI, they detected different patients at risks. So we analyzed the individual patients which were identified either only by the medical doctors or only by the AI-based system or by the combination of both. And you found that they work well on different types of data, on different type of patients in this case. So there is usefulness in combining decisions from AI and from humans when being correctly communicated between the two. And that's an active field of research in our community and in our group here as well, of how can we optimally combine the performance of an AI-based system and the performance of humans who need to take decisions, for example, in a medical use case, but we are also working on fake news detection, for example. We also want to have a human taking that decision on, for example, banning a user. How can we optimally combine that by making AI explainable and in this way also trustworthy? So these were the aspects I wanted to highlight using speech and language technology as an example. And I know that many of these questions also pop up for the visual domain. So I'm happy to also answer questions which are related to that, and perhaps leave it also to Rita to answer those questions. Thank you very much.
So thank you. Yes, so I have a few questions, but let's see what is there. So maybe I wasn't completely clear. You could have asked questions also during the talks, but you can do it right now as well. So on the right hand side, speaking to the audience, obviously you can write down your questions. In between, while we are waiting, I don't know, should I begin, or maybe Vincenzo, do you want to ask something? So I will begin asking a question to Sebastian about the last things he said. So first of all, in your slide 28, I think it was, you still have your, can you still show them, or do I have to give you the word again, the screen again?
I can show them again, I think.
Yeah, you should. Okay. So where you had this, exactly this one. So it's not clear. Two things I would like to understand better. First of all, what features did you use for your predictor? So each time, these are time points, what we are seeing, right? So the blue points. So these are the points where the patient is being, let's say, seen by the doctor.
Exactly, right. Exactly. These are the points where the doctor sees the patients, and there is a certain risk score being built on the basis of either local measurements which were performed at that time. So the blood, whatever was investigated, something, and then there are some more global features we know about the patient, about the history of the patient, and taking both and putting that into a neural network would give us this risk score. Now, so, the doctor, of course,
as input you don't. Sorry. As input you don't use also some judgment of the doctors. So it's just, let's say, objective measurements.
In the prediction, yes. In the prediction is objective measurements. What we want to have is this system communicating with the doctor in some way, either through the dashboard. Ideally, the doctor could also say, if the blood level at that point was lower than, what would be your prediction of the risk of the loss of the kidney, for example? Or why are you predicting a loss at this certain point in time, not only listing the features which were used for this purpose, but also explaining in words what the reason behind the decision of the system or the prediction of the system would have been. That is the ideal system I would see, like a companion to the doctor, where the doctor can ask, why is the system predicting a certain thing?
And I was a bit puzzled, but maybe it's normal that it's the last point. So after such a long time, you have a risky situation. Is this? I would expect that you have it at the beginning, but this is not the case.
Yeah, apparently not. So these are real cases which have been collected over a couple of years. You see that the data is quite old in Charité. So that was data which was available for us, and of course we did a proper separation of training and testing data in order to test our system on that data. So apparently, I'm not a medical expert, but apparently there are risk factors which happen after a certain time that an organ like a kidney is being rejected, and it's not something which is visible from the very beginning.
That's bad for a patient, yes.
Yeah, is it so what you plan to do? So essentially these data points are collected for a certain period, and then at the end, either the AI or the medical doctors or both are doing the predictions. That, if I understand correctly, what you would like to do, I suppose, is a sort of Bayesian adaptation, like, you know, what would the doctor say if he knew up to that point, and then, you know, feed the thing back into the prediction along the way to then.
No, the setting, I mean, the ideal setting would be the doctor has a tool, the doctor has his own view, and of course the decision is with the doctor. It's never the system deciding on any treatment or therapy or something like that. But the system should support the doctor. And the system can do that with the history of data it has, and it can make the predictions explainable to the doctor. And that is actually our point. We want, of course, to have a system which does an optimal performance, but at the same time, we want to have a system which also explains the basis of that performance to the doctor, so that the doctor can bypass the system. It can override the system decision in a reasonable way, because the doctor understands why the system has done this prediction, and perhaps the doctor has different evidence, has newer evidence which was not in the training data, and then you would have an optimum cooperation between the human and the system.
Just another question is, so the features, you know, the various objective values are, well, the typical values of that a doctor would consider, I presume, or is there some latitude in this choice, like you could choose more data or less data or different data?
No, this was data which we actually had available. So there is the question of availability of data, and that is data which was considered to be useful by the expert from the Charité Hospital.
Okay. So I still don't see questions from the audience.
I think I tried to ask a question my own. I couldn't type in anything. Perhaps it's the same problem for the others. I don't know.
Can I ask a question to Rita? When she mentioned that since I am a computational scientist myself in a different area, and I worked at CINECA for many years. So you mentioned that you have a heavy computing load. So is that, so let's say one thing is that related to constructing, optimizing the neural networks, or to other features? And second, are these algorithmic problems parallel to some extent, or completely, or how does it work?
Yeah, can you hear me?
Yes.
Okay. Yeah, now I think that if you want to go in the direction of large-scale models, you cannot stay without a parallel GPU system large like a supercomputer center. So in the last 3 years, especially because in Modena we have the lab with NVIDIA also, we are working together and together with the CINECA in order to parallelize our algorithm. Using GPUs in parallel now is absolutely necessary, especially if you want to train with millions or billions of data. So the most important things is that you can, in general, you can think about the algorithm before, test it before in a smaller service like the one we have. We have a good GPU service in our lab, but then at the end, when you want to do a large training, you need to go them. Just to give a publicity to all the people connected, especially in Germany, because I think the people in Italy, they know already. In September, the third week of September, we will have in Modena the Ellis PhD school on large-scale AI. So that is open, for Ellis PhD students, but actually is open to all the PhD students that are interesting if there is enough space. Because we will have the connection with Cineca, and so Cineca will put availability of hundreds of GPUs in order to work in parallel with them. So this is really important now for the students to learn how can deal with parallel learning, and so this is a part that for us is very important now. You cannot stay without if you want to go in this large-scale world. Of course, it's not necessary, and we don't want to compete with Google or with OpenAI and so on, because we are studying small problems that sometimes are not addressed in this large scale. But then when you want to test them, you need this power. Unfortunately, in Europe and in Italy, we have now.
I'm just wondering, are these the algorithmic problems you are dealing with embarrassingly parallel, not parallel at all, or a combination of the two?
The learning step can be done in parallel in many cases. Now, I'm studying computer architecture in my first life, and but now we don't do anything in this area. So we use the tools that NVIDIA provide for us. But without this possibility, it's not possible to train in acceptable time, I say, because already if we use a parallel GPU, we must wait days or weeks because before having a number. So we need to use them. When at the end you want to do final experimentation during the standard study, instead we can really stay without. So that is, there is a lot of room for this kind of research in parallelizing this algorithm. We don't do that. We use the tools actually.
Okay, thank you.
We have the first question for Sebastian Möller. Nicola Mosca asks, just out of curiosity, while anonymizing, why anonymize parts like I am Möller and change it in I am Briley instead of skipping them? If there is no way to check the truthfulness of the info given, what is the value of that information? So why don't you skip that information in spite of changing to an anonymous name, I guess? This example, actually, Max Mustermann, that's the typical anonymous name in Germany. So it's kind of, I don't know, there's kind of
Mario Rossi.
Mario Rossi in Italian. Yes.
Even more generic.
So that was an example. It depends, of course, on the purpose of what information you need to disguise. This was just an example that in addition to the anonymization on the signal level, you also need to do an anonymization on the contextual level. Now, the question is, how critical is the name? Can I guess perhaps the origin of that information already from other information? I mean, if I'm working at a technical university, then the probability of being male is much higher than of being female. If I have a certain age and a certain gender and certain other characteristics, then you might still guess the identity of the source of that information. Same for location information, for example. So there are different types of information with different criticalities, and we're also trying to analyze what is important or what is critical for a user to not be shared, and what other information might be something you are easy about sharing. For example, your medical circumstances might be something which seem critical to you. For some others, gender might be something critical. So this really depends on the situation, whom you want to share with something or not share with something.
I guess that in that case, the question was why changing the name to a generic name and not completely leaving it out.
Yeah, you could, if you want to, if you have a human recipient of the statement afterwards, then it would seem odd a little bit if you just leave out information. So you would rather put that to a generic name in order to keep the structure of the sentence. If that is conveyed to some therapist on the other side, and the therapist has to act on that. So the scenario is basically that you have a chat interaction or a speech interaction between the therapist and the patient. And then you want to have kind of complete sentences on both sides.
Yeah. And maybe you can take away the information of the actual name, but you can still have the intonation on if you are producing speech, maybe.
Exactly, the intonation is important, for example, for conveying emotions, and the emotional state is something very important in a therapeutical discussion. So that's actually something we definitely need to keep. Other aspects, so the emotion, for example, can be interpreted much better if you know that this person is a heated Italian, or whether it's a very calm German, to be in the frame of this webinar. So this is something, so you need to interpret reactions from users according to the background which you would expect from that user. It might not always be correct, but at least you have expectations, and you need to have the background of that interpretation. So if I change the name to Max Mustermann, I would still assume it's a male person. I could also change it to Lisa Mustermann, and then I would probably assume that it's a female person. So depending on how you disguise, you create different expectations from the users or listeners of that utterances.
Right. Yeah. Okay, so I have let's say a street question. I don't know. So a very, let's say, non-technical question for Rita. You showed us a captioning of a video, of sort of different frames of a video. Mm-hmm. So I was thinking, is there, maybe there is already, is there already commercial, let's say, examples of this? I'm thinking of YouTube. Does YouTube do something like that?
Yeah. We are working a lot in the past, but also now in video captioning, because in video you can do in two different manners. You take some keyframe and represent them, and then you skip to the other one. And so this is something that is done in YouTube, for instance, in many other summarization of video system that select the most important keyframe and represent them. Instead, video captioning is more because take into account also the action and the action that are moving during the frame. So the video captioning is providing differently because you don't use just only one key, but use also the motion and optical flow information, for instance, embedded in neural network, but the idea is to use that. And so the idea is also to represent a part. I tell you that because in one of the new PNR, so next generation unit project, we have always coordinated by CNR. Okay, one of my cats is going, sorry. This is called the Fit for Med Rob. We are studying the interface between human and robots in dialogue. So one important thing is not only to produce caption of what you see during the time, but also when you have to decide to speak. So because you say, let's consider a robot that is going around, he cannot continually representing what they say, but so one work we will present next month in ICRA, so in the robotic conference, is also the one idea to decide when something is changed in a video, so it's better to represent it. So the problem in video are two. The one is to continuously understanding what's happened during the frame, and also decide when is going or not. In this case, there is nothing commercial now, at least in my knowledge.
And for the search, I mean, is it used or
for sure? Yeah, Google is using that. Google is using that because also you know that in Google now there is also the possibility to do search by images, but they don't publicize that. They don't want that people use that because from the bandwidth is a mess. Think if billions of people put on the web an image to ask, tell me something similar. So that
this is Google Lens. You are speaking of Google Lens.
They collapse. People from Google said that it's impossible. So this is available if you want to find similarity, and they use internally. But for a query, it's absolutely better to use text because text is more synthetic and few bits are transferred and so on. So they really use, not only Google, of course, use captioning as a sort of, I say metadata, but it's not a metadata, it's a description of the data that are useful for retrieval. And most of the system of retrieval now are multimodal and start from text and then go to image and go back. I have PhD students that are working in retrieval. That is one topic that I like. And but the problem is the correspondence, because as I said, if you look at an image, you could say many different descriptions of the same image. Or use like a GPT and you start, but you can start to talk in many different situations. If I look you, I can say there is a person in foreground with some books in the background, or I can focus on your glasses, or I can focus on the books. So I can say many different things. So for this reason, I say text is more synthetic, but sometimes too much with respect to the richness of the content of the image. As Sebastian said before, in speech, for instance, you have other human information, like I say, the personality or also the gender or whatever of the person. When you think about vision, there are a lot of details that are also connected with your attention, with your background, with many different things. So probably I see that you have, say, Madonna in your, because I'm Catholic, so I can recognize it. Other people probably they cannot recognize it. So this is something that is very interesting. That it's a long story and must be absolutely explored.
Okay, so is there a possibility, for example, referring to the video, the frame that you showed with Julia Roberts, for example, can I at the present time say to Google or something like that, find me the film or the movie or the moment in the movie where there is a woman carrying bags and there's a man in front of her carrying even more bags?
Okay, in this moment, Google do not provide this system, but they have that. So if you can go in Google image search, you can find this kind of things. Yes, you try it. Is doing. Also, my system is doing now, because even if with the new methods that have been trained on 32 million of pairs of images and text, there are so many web pages with Pretty Woman. Probably I don't know about exactly this frame, but in general it can be recognized. I didn't try it with that, but with many others that can be recognized because of the power of large scale model at the end. So the capability of put together a clip is fantastic for that. CLIP really is a trained system that now we use a lot because the latent space created by CLIP put together text and visual information in a space where it's really very close. I will try to see if it's able to, but you can have some services are already available.
All right. Okay, thank you. There are the second question from the audience. Faisal Rashid asked two questions. The first one to Rita: what are the advantages of controllable captioning? And second, how can we compare generated caption with human captions? As humans are very subjective and the captions by human may not be similar. What about telling a story based on an image? Remember, in our school days, we used to write an essay based on an image. Okay, so let's go. What are the advantages of a controllable captioning, and how can we compare generated captioning with human captions?
The two questions are actually very related. Technically speaking, having the possibility to create a controllable caption by content can go in the direction to create a different caption according to different intention, different tasks. For instance, you can, and this is the reason where captioning can be useful, because for instance, you can decide to say, tell me just only something about the cars that are around you, and that can be used in automotive in order to understand the traffic. They don't care instead about the buildings that are around, or tell me something about just all the people that are there, or tell me something about so controllable captioning means I have a method to control, to guide the caption according to some visual objects or something that has been detected. So this is a way to go on that. And for instance, Google is using something that is very Vito Ferrari in particular. They are using something very similar to what we presented in 2019 because is an evolution of that. But the second question is really important. How can you compare captions with the human captions? It's I say impossible in general. In the computer vision community, as I told at the beginning, most of the people use COCO dataset, but I say stupid because in COCO there are just only 5 captions taken 6 years ago by people, and you could have 1 million of captions similar of that. But from the comparison of the techniques, most of the people are using that. But now, for instance, the manner that I briefly described about the new measure packs that we proposed is the idea to enlarge the capability using synthetic text generator and synthetic image generation. Because since synthetic text generation and synthetic image generation mimic so well human behavior, now we can have something reproducible. Otherwise, we have to take 1 million of persons and ask them, but as I told, it cannot be afforded often.
Okay, thank you. And the same person, Faisal Rashid, asked a question to Sebastian. How well is your system received by the medical doctors? Are they willing to use it in the real practice? What kind of regulations you need to meet to get approved for the clinical usage at large?
So the medical doctors we have been in touch with, they were quite open to using such systems. They could imagine that if it performs well and if they have evidence also for performing well, that they use it. But of course, you have seen that the reception of the system or the impact of the system might be different according to the experience of the doctor. I think we are still very far from using that system directly in practice. First, because it's a medical support system, and medical support systems have to undergo all these evidence trials, which you have to carry out with real humans, with real patients. And so you need lots of evidence in order to make something allowed to be used in a medical use case here. The second point is that our data has actually shown that the interface we have is not ideal. It's not ideal for catering for all types of doctors. So either we would need to make it adaptive, or we would need to change the interface so that users can really, the doctors can really find out about the basis of the decision. I think as long as this is not done, there is no chance to see that system in practice. But I think we need to do more trials like this, to do more, to get more data in order to find out what the important criteria are, and then we can come up with something which can undergo a process of being accepted at large scale.
So the question is, are you following?
Sorry for both, for all the people, but I really have to go because I have another call now. I'm so sorry, but really I have to say you ciao, and thank you a lot for the invitation. And
thank you very much, Rita. We keep in contact, and anyway, we are nearing the end. So thank you, and we continue the questions with Sebastian. Thank you very much. So I was asking you, are you following up? Are you following up on this project? So in order to do these steps, or do you know somebody who already is further than you and in this sector, so that the AI system is really used already in the practice?
Yes, so we are following up. We have a follow-up project to the Valid project. That's the result I represented. So there is a current follow-up project running, again with the colleagues from Charité. So if you want to have more information on that, perhaps be involved in some of that, please just send me an email, and I would direct you to the colleagues directly working in the project. Definitely yes. Actually, we have seen we've now a couple of collaborations with Charité, and we see that medical doctors, at least here in Berlin, they are really open towards the use of these technologies. Not only AI, we were mostly on AI, but also virtual reality, extended reality stuff. So there is a strong push also from the user side, from the doctor side, in making use of these technologies. I'm rather optimistic that we will see such systems in practice rather sooner than later. Although I know that the processes for being introduced, they are very slow in Germany as everywhere else. But I'm quite confident, because there is a real gain to be reached through these systems, I think.
Okay, so I'm saying it for the CNR audience. The Charité is, I think, the biggest medical university in Europe. So I mean, Sebastian has a good basis for his work in cooperating with Charité, and Charité and the TU, the Technical University, and for example, Fraunhofer, we listened to Wojciech Samek last week, are part together of this bifold center in Berlin, which is one of the 5 in Germany, but I guess it's the one with the biggest medical partner. I would guess. I don't know. I don't think that the other have a medical partner which is as big as the Charité. Right. So if you are interested in cooperating on AI linked to medicine, I would think that Berlin and Bifold and, for example, Sebastian and others for sure are a good let's say contact point.
True, and there, so as the DFKI has a 3 research departments in Lübeck, which are concentrating on medical AI, on different aspects, vision or image analysis and other stuff. So there is also in DFKI, there's another group. It's just located in Lübeck, north of Germany. Mm-hmm.
Okay, Lübeck is a very nice city, by the way. So, okay, yes. So at the end of this seminar, so in the next days, I mean, I will send the slides, the link to the recording of this webinar, and I will CC the speakers. So that if you want to follow up with some of them, you have their contacts. And I ask you to let me know, so that the International Relations Office of CNR know if something comes out of possible contacts that you will have in the future. so that we are aware of also of the advantages of having these webinars, let's say. Okay, so I see there are no more questions. I don't know, Vincenzo, do you have a question?
Yeah, the couple. That's fine with me.
Okay, so I guess it's 1 minute before 12, so we are in perfect time, but in the maximum. So we use the maximum time we had. And Sebastian, thank you very much. And we keep in contact for the next for the DFKI CNR business. We talk in the next days. Okay.
Thank you for the invitation.
Thank you very much.
Thank you.
And
Bye.
thank you to all the audience, obviously. Bye bye.